Welcome back to AGRON Info Tech. In the previous video, we learned how to nest country data and fit one linear model per country. In this chapter, we take the next important step. Instead of focusing on one country at a time, we compare coefficients and model fit across all countries. This turns a single model workflow into a mini-model tidy machine learning workflow. First, I'll load the required packages. I use Tidyverse for data wrangling and plotting, Gapminder for the public country-level dataset, and Broom for converting model results into tidy tables. These three packages work very well together because Tidyverse handles the nested workflow, Gapminder provides repeated country observations over time, and Broom makes model summaries easy to extract and compare. Next, I prepare the data in a clean, teaching-friendly format. I use transmute because I want to keep only the variables needed for the lesson and rename them at the same time. I keep country, continent, and year, and I rename life expectancy, population, and GDP per capita into clearer variable names. Then I group the data by country and continent before nesting. I specify those grouping variables because they are the identifiers I want to keep outside the nested cells. After nesting, each row represents one country and one continent, while the remaining time series columns are stored inside a list column called data. Now I build one linear regression model per country. Inside mutate, I use map so that each nested tibble is sent into the same model formula. The formula predicts life expectancy from year because this chapter is about comparing long-term time trends across countries. The data argument tells the model to use each nested country tibble separately. After this step, I have a tidy table of countries with one model stored in each row. Now I extract model coefficients from all of those country models. To do that, I use tidy inside map because tidy returns coefficient level output as a small tibble for each model. Then I unnest the coefficient tables into one combined data frame. This is one of the most useful parts of the tidy workflow. Instead of hundreds of separate model summaries, I now have one clean table with all coefficient results together. When I print the first few rows, I see both the intercept and year coefficient for Afghanistan, Albania, and Algeria. For Afghanistan, the year slope is about 0.275. For Albania, it is about 0.335. For Algeria, it is about 0.569. These values mean that, on average, life expectancy in those countries increases by about 0.28, 0.34, and 0.57 years for each 1 year increase in time. Algeria stands out immediately as having a much stronger upward trend than Afghanistan and Albania. Next, I draw a histogram of the year coefficients. Before plotting, I filter the coefficient table to keep only the rows where the term is year, because that is the coefficient we want to compare across countries. In the plot, the horizontal axis shows the slope for year, and the vertical axis shows how many countries fall into each range. The histogram tells a very clear story. Most countries have positive slopes, and the bulk of the distribution sits roughly between 0.2 and 0.5. There are only a few countries near 0 or below 0, and there's a long positive tail reaching up toward about 0.77. So visually, the chart already tells us that life expectancy usually rises over time, but the rate of improvement is not the same everywhere. Now, I study the year coefficient more directly. I filter for the year term again and arrange the rows in descending order of the estimate, so the largest slopes appear first. The output shows Oman at the top with a slope of about 0.772, followed by Vietnam at about 0.672, Saudi Arabia at about 0.650, and Indonesia at about 0.635. These are some of the strongest upward life expectancy trends in the dataset. Oman is especially notable because its slope means life expectancy rises by roughly 0.77 years per calendar year in the fitted line, which is a very steep increase over this period. Then I summarize the year slopes numerically. The minimum is about negative 0.093, the first quartile is about 0.208, the median is about 0.321, the mean is about 0.326, and the maximum is about 0.772. This confirms the visual pattern from the histogram. The average country has a positive upward trend of about 1/3 of a year of life expectancy gained per year, while only a very small number of countries show negative trends. To make that even clearer, I calculate the percentage of positive and negative slopes. I use a logical comparison inside mean because true values are treated as 1 and false values as 0. After multiplying by 100, the output shows that about 97.89% of countries have positive year slopes and about 2.11% have negative slopes. This is one of the key takeaways of the video. Across the Gapminder data, life expectancy improves over time in almost every country, but the strength of that improvement varies widely. At this point, I correct a small issue from the original workflow. If I use slice_max while the data is still grouped, it returns one row per group instead of the single global maximum. So before selecting the top country, I remove grouping with ungroup. After that correction, slice_max correctly returns Oman as the country with the largest year coefficient. That fix is important because we want a single strongest slope overall, not the top row inside every group country. Now I move from coefficients to model fit. I use glance inside map because glance returns one row model summaries. Then I unnest those results, so each country has fit statistics like R², adjusted R², sigma, and AIC in a tidy table. When I print the first few rows, I see that Afghanistan has an R² of about 0.948, Albania about 0.911, Algeria about 0.985, and Argentina about 0.996. These are already strong fits, especially for Algeria and Argentina, where a simple straight-line trend captures most of the variation in life expectancy over time. Next, I create a histogram of R² values. The horizontal axis shows model fit, and the vertical axis shows the number of countries. This plot has a very interesting shape. Most countries cluster very close to 1.0, which means a simple model using year alone fits surprisingly well for many countries. But there's also a small set of countries far to the left with much weaker fit. So this chart tells us that a straight line works very well for many countries, but not for all of them. Now I compare the best and worst models directly. Before selecting them, I ungroup the data so the ranking works across all countries. Then I use slice_max to get the 4 highest R² values and slice_min to get the 4 lowest. The best fitting models are Brazil, Mauritania, France, and Switzerland, all with R² values around 0.997 to 0.998. The worst fitting models are Rwanda at about 0.017, Botswana at about 0.034, Zimbabwe at about 0.056, and Zambia at about 0.060. That difference is huge, and it tells us that not every country follows a clean linear trend. To understand why, I augment the best and worst models and then plot actual versus fitted values in faceted panels. In the best fitting country plots, the black points sit very close to the red fitted line. Brazil, France, Mauritania, and Switzerland all show steady upward trends with only small deviations. Visually, these panels look almost perfectly linear, which explains their extremely high R² values. The results show a clear improvement. Zambia reaches an adjusted R² of about 0.679, Zimbabwe about 0.589, Rwanda about 0.525, and Botswana about 0.163. Botswana still remains difficult to model, but the other 3 improve substantially. That tells us the added predictors capture important structure that the simple time-only model was missing. So this chapter teaches 2 important ideas. First, tidy modeling lets us compare coefficients and model fit across many groups in one organized workflow. Second, model interpretation becomes much stronger when we combine coefficient tables, summary statistics, and visual diagnostics. In the next video, we shift from descriptive model comparison into predictive workflow design with training, test, and validation splits.